There are 5, or 6, or 7, or 8, or 9 planets in the solar system. The actual answer depends on the time period in which the question was asked. Currently, in 2025, and based on a specific definition, we have 8. Before the early 1990s, you could ask the same question without having to add the qualifier in our solar system. At that time, planets existed only in the solar system. Yes, we had no reason to believe that planets did not exist in other systems. But when confronted with the question, where's the evidence? The diehard would say, I just know it in my heart. Unfortunately, we could not get radius, mass, or other basic data about exoplanets from the human heart. We had to wait until we invented reliable methods to not simply detect exoplanets, but more importantly, collect data like radius and mass. Data that, when combined with our existing knowledge of the universe, gives us a better understanding of that universe. The question about the existence of planets outside of the solar system is similar to the existence of life outside of the solar system. Once again, there is no reason to believe that life does not exist in other star systems. But for now, we have no evidence, nothing, nicht, nada. We do have various hypotheses that attempt to describe the probability of life outside of the solar system. But just knowing the probability of something existing tells us nothing useful about said thing. I mean, we could speculate about alien life being something that's easy to visualize in theaters, TVs, and even YouTube videos. But at the end of the day, we know nothing, nicht, nada, about alien life forms until the evidence starts coming in. We'll tackle this issue in a future episode of Celestial Sphere. But what you're currently watching is not Celestial Sphere. This is an episode of Sensing the Universe, a series that deep dives into the instruments that we use to detect and measure things in the universe. Is there now an instrument that can detect life remotely outside of Earth? The answer is obviously no. But the original question was about the existence of planets outside of the solar system. And that has not been completely answered. All exoplanets detected so far are located in star systems that are only within the Milky Way galaxy. Can planets form in star systems in other galaxies? There is no reason to believe that they cannot. But once again, we have no solid evidence. That is, until a few years ago. We may have evidence of a planet in a galaxy far, far away. It's called M51ULS-1b, and it's a candidate for the first exoplanet detected outside of the Milky Way galaxy. This potential planet has been detected in a galaxy called Messier 51, sometimes called the Whirlpool Galaxy. It's about 31 million light years away, and it's 3/4 the diameter of the Milky Way galaxy. Actually, the Whirlpool Galaxy is made of 2 separate galaxies, Messier 51A and Messier 51b, its companion. Messier 51A is the larger of the two, and that's where the potential exoplanet has been detected. The smaller galaxy, Messier 51b, is in the process of merging with the bigger one, and this interaction is potentially triggering a large amount of star formations. When galaxies merge, there's very little chance that the individual stars within them will directly collide. However, the relatively rapid change in gravitational potential and the mixing of interstellar clouds from each galaxy can trigger massive interstellar clouds to start condensing into star systems. The process is extremely complex and is not properly understood. Under these conditions, what kind of stars can be formed? what kinds of planets, if any, can form around these stars. We know a little bit about the kinds of stars that can be formed, but when it comes to the planets, we know nothing. It's very difficult to detect individual stars in other galaxies, let alone planets around those stars. We can detect individual stars in close-by galaxies like Andromeda, which is in our backyard at only 2.5 million light years away. But these stars are all giant ones. The more massive a star is, the harder it is to detect planets using the radial velocity method, which directly depends on the mass of the star. The transit method for detecting planets does not depend on the mass of the star, but since it's based on the dimming of the starlight by the planet, it depends on the distance to the star. The further away the star, the less light is available to detect the dimming. In addition, there also needs to be an alignment between star, planet, and Earth for this method to work. So how is it that we can potentially detect a planet that is a little over an order of magnitude further away than the Andromeda Galaxy, 31 million light years from Earth? How is that possible? The key to this answer is X-ray, how they're produced in certain celestial objects, and how we detect them. X-rays are high-energy photons. In nature, they're either produced through radioactive decay or extremely high-energy interaction of matter. The X-rays that we detect from space are all produced in an extremely high-energy environment. These include environments with extremely high temperatures like the ones found in white dwarfs or supernovae. They're also produced in environments with extremely high gravitational fields like a black hole, or environments with extremely high magnetic fields like a neutron star. As stated earlier, one of the ways to detect a planet orbiting a star at great distances is to measure how much the light from that star is dimmed when the planet eclipses the star. This is called the transit method. But for this to work, the orbital plane of the planet must align with the plane that the Earth and the star are on. This requirement alone makes it impossible to detect planets in most of the star systems. But this is not really a drawback because just in the Milky Way alone, we have at least 200 billion stars to choose from. Surely we can expect at least 500,000 of them to be in alignment with us. Since the transit method is dependent on the planet eclipsing the star, the amount of dimming will depend on the diameter of the planet relative to the star. That is, the bigger the planet relative to the star, the more of the starlight will be dimmed during the eclipse, and the easier it will be to detect the dimming from other fluctuations in the starlight. So what does this all mean? It means that it's easier to detect bigger planets than smaller ones. But this also means that the further away a star is, the bigger a planet has to be relative to the star so that the dimming that it causes can be distinguished in the now smaller amount of light that's being received from the star. However, there is a limit to how big a planet can get, therefore putting a physical limit on how far we can detect planets orbiting a star. A smaller diameter star will usually have smaller planets because the dust and gas cloud that created the star system was also smaller. If it could have bigger planets, that would greatly increase the dimming effect without exceeding the maximum size possible for a planet. But it doesn't, so this wouldn't work. But what if we can increase the mass of a star, but somehow also greatly decrease its diameter at the same time? Now, if this were possible, it would allow the star to retain big planets already in its orbit, while at the same time, with its smaller diameter, allow more of its light to be blocked by the big planet, essentially making it easier for us to detect planets in orbit around it, even when we receive very little light from the star due to it being very, very far away, potentially as far as another galaxy. A star with the properties we've just described, massive but small, does exist in nature. It's called a neutron star. It's the remnant of the core of some massive stars after a supernova explosion. This star is mostly made of neutrons, hence the name. But the most important aspect of a neutron star as far as finding planet goes is that it emits most of its radiation in X-ray. So if we're going to look for planets around such a star using the transit method, we're going to need a good X-ray detector, a space-based X-ray detector, a powerful one like the Chandra X-ray Observatory. Interest in X-ray from space started in the 1920s when the U.S. Navy was interested in how they affected shortwave communications within the ionosphere. The ionosphere can reflect shortwave radio signals. Since this layer of the atmosphere is one of the outermost layers of the atmosphere, it is severely affected by radiation from space. While there was real interest in studying X-rays from space in the 1920s, it wasn't until 1949 that the first ones were detected. Early X-ray observations were conducted using sounding rockets on a suborbital trajectory. Because of this, observations were limited to only a few minutes. In 1970, X-ray astronomy took a great leap forward with the launch of the Uhuru X-ray satellite by NASA. Since the satellite was in space and above the X-ray absorbing atmosphere of Earth, longer observations of X-ray sources could be made. With longer observations, we were able to detect variations in the X-ray sources. 15 years after Uhuru was launched, so in 1976, NASA began work on an advanced X-ray telescope called Advanced X-ray Astrophysics Facility, or AXAF. Shortly before this telescope was launched into space in 1999, it was renamed to the Chandra X-ray Observatory, or simply Chandra. Chandra was the third telescope launched in the NASA Great Observatories program. First one was the Hubble Space Telescope, detecting invisible light and ultraviolet. Next to launch was the Compton Gamma Ray Observatory, detecting in gamma rays and high-energy X-rays. After that, Chandra was launched, detecting in soft X-ray. And finally, the Spitzer Space Telescope, detecting in infrared. The Chandra Telescope was named after an Indian-American theoretical physicist, Subrahmanyan Chandrasekhar. He contributed a lot to our current understanding of stellar structures, white dwarfs, stellar dynamics, and much more, including the Chandrasekhar limit, which is the maximum mass of a stable white dwarf star. Chandrasekhar contributed a lot to astronomy, so it's only fitting that a great telescope that also contributed a lot to astronomy and continues to do so today was named after him. Look at this collection of images taken by Chandra. They are truly amazing. But just to be clear, each image is multispectral. That is, it's a composite image taken from other telescopes at different wavelengths. These composites include images from visible, infrared, radio, and X-ray. Chandra provides the X-ray part of the image, and this is usually the blue, pink, and purple parts of the image. Many images from space are presented this way to give the viewer a more comprehensive view of the scene in the image. Using, for example, visible light only will not highlight all of the objects like gas and dust in the scene. Because of this, some people might consider these images to be fakes. Well, if they are to be labeled fakes, then they are as fake as the radiographs produced by a medical X-ray machine. Anyways, the Chandra telescope, like all telescopes, is at its most basic a device that collects energy from a wider area and then focuses that energy with minimal distortion into a smaller area to be detected by sensors. Usually, this is done by a set of lenses or a set of concave and convex mirrors. This is true for Hubble, Spitzer, and the James Webb Telescope. However, focusing X-ray this way would not work. That's because the X-rays would go right through or get absorbed by the lenses or mirrors of these telescopes. The end result is that the X-ray won't be focused to form an image. The key to focusing X-ray in Chandra is to use a series of mirrors at a very low angle or grazing angle to the incoming beam. How and why that works is the key to understanding X-ray telescopes in general. This may get a little complicated. We stated earlier that we needed a series of mirrors to focus the X-ray. This would work if we lived in a two-dimensional world. In a three-dimensional world, we need a series of mirrored hollow cones to do the job. To be exact, we need 8 of these reflecting cones. They are divided into 2 sets of 4. The primary set of mirror cones is not exactly a cone, but a section of a paraboloid, the 3D shape created when a parabola is rotated around its axis of symmetry. The secondary set of cones is not exactly a cone either, but instead, it's a hyperboloid, the 3D shape created when a hyperbola is rotated around its transverse axis. If they were just cone segments, then they wouldn't properly redirect the X-rays to the focal point. But we'll still call them cones for simplicity. Each mirror set contains 4 of these cones laid out concentrically. The reason for having 4 concentric cones is to maximize the amount of X-ray collected and focused on the detector. Since the X-ray can't be bent by going through a glass lens, and it can only be reflected from a mirrored surface at a shallow angle, the only way to practically increase the X-ray gathering area is to have concentric reflectors. These cone segment reflectors in Chandra range in size from 0.6 meters to 1.2 meters. They are made from a very low thermal expansion glass called Zero-Dur. That's the commercial name. Very low thermal expansion lenses and mirrors are required in every space-based telescope because of the extreme temperature swing that it goes through during normal operation. Finally, the Zero-Dur glass is given an iridium coating to maximize the reflection of X-ray. The 2 sets of mirrors are located in what is called the High Resolution Mirror Assembly, or HRMA. The HRMA also includes thermal collimators at multiple locations. The collimators absorb stray light, preventing them from entering the HRMA, where they would not be useful in creating an image, but would still add heat to the telescope. In effect, it shapes the incoming beam, letting in only those that are useful in forming an image. Now, with the high-resolution mirror assembly explained, let's follow the beam to the sensors. The primary sensor is called Advanced CCD Imaging Spectrometer, or ACES for short. There's also a secondary detector called High Resolution Camera, or HRC. Let's start with the HRC because it behaves more like a photometer than a camera. A photometer is an instrument that only detects the intensity of a light source and not its color, i.e. frequency. But for what the HRC lacks, it excels when it comes to creating an image with a high spatial resolution. That is, creating a sharper image with more detail. The HRC has 2 detectors, HRC-I and HRC-S. Let's start with HRC-I. It has the sensor size of 100 millimeters by 100 millimeters. It's primarily used to take a wide field of view image. For example, imaging supernova remnants or galactic jets. HRC-S, on the other hand, is geared towards spectroscopy. That is, detecting individual X-ray frequencies and their corresponding intensities. That's what a spectrometer does. In X-ray spectroscopy, the frequency of the X-ray is stated in terms of the amount of energy the individual photons have. This is stated in kiloelectron volts, or keV. Just a side note. HRCS has a sensor size of 20 millimeters by 300 millimeters. Since the HRCS sensor itself cannot detect the various X-ray energies falling on it, we have to use a special diffraction grating that is swung into position to separate the various energies. The same way a prism can be used to separate white light into spectrum colors. The various X-ray energies will then be spatially spread out on the detector like the color of the spectrum through a prism. While the detector will still perceive intensity only, the spatial separation on the detector will be used to determine the energy of the signal at that location. The HRCS is not used to create a normal image of what's out there in space, but is usually used to collect thermal data about a particular celestial object like a binary star or a black hole. The detectors in HRCI and HRCS are both microchannel plate detectors, or simply MCP. A while back, actually 5 years ago, I covered a detector on the Messenger spacecraft, the neutron spectrometer. It detected neutrons by letting them hit a special surface called a scintillator. The impact of the neutron caused a photon to be emitted. This photon is then passed through a photomultiplier tube, which will cause the release of many electrons that will ultimately be detected as current flow in the electronics. A MCP is similar, but instead of having a single photomultiplier tube, it can have millions. These are microscopic tubes, hence the name. The MCP detector in the HRCI instrument has 69 million of them. When X-ray first enters the MCP detector, it passes through an ultraviolet light and ion shield. This is necessary because the actual MCP is also sensitive to ultraviolet light and ion. So they must be blocked. Next, the X-ray hits the cesium iodide layer. The X-ray is mostly absorbed and causes this layer to emit electrons. The electrons are then directed into the first of two microchannel plates. These plates contain millions of tubes with a diameter of only 10 micrometers. They're slightly slanted from the direction of the incoming electrons. Each time these initial electrons hit the inner wall of the microtubes, they cause secondary electrons to be emitted. Those secondary electrons hit the wall. They also cause secondary electrons to be emitted. A cloud of electrons emerges on the other side of the tube from a single incoming photon. This cloud is amplified even more when it passes through the second microchannel plate. In the end, a large amount of electrons are ejected from the interaction of the single photon, about 20 million electrons. This cloud of electrons, now at the final stage of the detector, passes through a grid of wires laid out like a graph paper. One set of wires represents the x-axis, and the other set of wires represents the y-axis. As the electron passes near or hits a wire, they induce a small current in the nearby wires. These small currents are amplified, sometimes digitized, and then sent to a computer. Based on the X and Y wires that have current flow at a given time, the location of the cloud on the grid can be computed, and an image of what the telescope is looking at can be created. Now, let's take a look at the HRCS detector. This is also a microchannel plate detector, but instead of it being a single square-shaped detector like the HRCI, it's a set of 3 rectangular-shaped detectors with a size of 18.6 millimeters by 100 millimeters each. Since the HRCS is a spectrometer instead of an imager, the incoming X-rays are spread out over a wider area because of the special diffraction grating that is placed in the path of the incoming X-rays when this instrument is used. 3 detectors are used instead of 1 because the ideal detector needs to be slightly curved. But since these are flat detectors, the only way to achieve this curving is to use separate detectors tilted at specific angles. Another reason for having separate detectors instead of just 1 is that since the various incoming X-ray energies are spread out on the detectors, each detector can be optimized for the frequency it is expected to detect. Lastly, The center detector in the HRCS can be used as a backup detector for the HRCI, since they both have their geometric centers aligned with the optical center line of the telescope. The HRCS is designed to study, among many other things, the structure, internal composition, and temperature of celestial objects like black holes, neutron stars, supernovae, and others. Let's finally look at the ACES sensor. This sensor, like the HRC, also has two detectors, ACES-I and ACES-S. It's used to also create images from X-ray emitting objects and can be used as a spectrometer. The main difference between HRC and ACES is that ACES uses charge-coupled devices, or CCD, on its detectors instead of microchannel plates. In addition, ACES has a much wider field of view than HRC. These differences make ACES more suitable for simultaneous imaging of many celestial objects, detect higher energy X-rays, and measure the X-ray energies directly. In ACES-I, there are 4 square CCD detectors. These CCDs directly detect the X-rays in the following way. Each ACES detector has 1024 by 1024 pixels, or light detecting elements. When an X-ray photon hits a pixel, it ejects a certain amount of electrons from the surface material and is stored in the layer underneath. Essentially, the layer underneath gets charged. The amount that is charged depends directly on the incoming energy of the X-ray. Each pixel also has a control line. After a certain amount of time of collecting the electrons, the charge on each pixel is read out. A 1024 by 1024 sensor has over 1 million elements. This means we would need at least 1024 times 2 connections to the sensors to access all the pixels. But the way the CCD is designed, all pixels share the same output wire over time. By applying the proper control signal, each pixel in a row will transfer its charge to the neighboring pixel. Essentially, they're coupled, hence the name charge-coupled device. The pixel at the very end of each row will then transfer its charge to a special shift register that will hold the charge. This shift register will then output those end charges that came from each row one at a time. The charge is then converted into a voltage and then sent to an analog to digital converter. After that, it's fed into a computer, which will then process the data to create an image, a graph, or other types of representation of the data. In ACES-I, there are 4 square CCD detectors arranged in a square. In ACES-S, there are 6 square CCDs arranged in a single line. Just like the HRCS, ACES-S is used as a spectrometer. That's why it has a similar shape. ACES-S doesn't need a diffraction grating to function, since the CCD can directly detect the energies of the incoming X-rays. However, it performs better with the diffraction grating. And now we come full circle. It was ACES-S that detected the potential exoplanet M51 ULS-1b in the Whirlpool Galaxy. If it's proven to be an actual planet, then we already have data about it. I'm DexDFX for Sensing the Universe.